All right, let's look at section 15.3, and this is about integration in more than two variables, or in three variables, and it's basically the same idea. So instead of starting with rectangles, what we start with is let's start with boxes, right? So that's the three-dimensional version of a rectangle, right? Now, before a rectangle, we cut into many small little pieces. Well, you do the same thing. It's you cut this into little cubes, and it's hard to draw, but hopefully you get the picture. You cut into small little cubes, and then if you have a function, so this is a box, let's call it B, and what we'll say is the integral of some function of x, y, z, three variables. With respect to now, we're going to write dv, right? What is this? Well, this is really the, let me just be very vague, limit of this delta v going to 0, where delta v is the, if I look at one of these little boxes, right, it has volume delta v, right? Really tiny box, tiny volume, and each one of these there is a point p. Let's call it p I j k, because there's really going to be three different. I have the rows, the columns, and the levels, right? However you want to write it. So I have, let me just write it as a sum I, j, k. Let me simplify the notation over here. So we have a sum of all these little, over all these little boxes, right? And we're looking P evaluated, F evaluated at this P, I, j, k, right? So on some point inside, right, and then we're multiplying by the size of these little boxes. So that's really what the integral is. It's very similar to before, except now it's really over three different. There's I, there's j, there's k. So that's the only difference, really. All right, so. Again, this is not really the way that you compute these things. This is what it is. So maybe if you're modeling, if you're trying to figure out how something works, you're trying to figure out some physical law, or trying to figure out how your model is going to work, how your what you're actually going to be computing. You might find an expression like this, and then you say, "Hey, I know that. That's the integral." But it's not the way that you compute it, unless unless this f is something really ugly. If it's given by data that you get from the real world, then or something like this is essentially the best that you can do. But if you have nice formulas for f, maybe we can use calculus to compute these things. All right. Now, before we get to that, let's maybe think about what does it mean, right? Maybe it's a little harder to maybe see this. Before we had the integral of a function of one variable. That was the area under the graph, right? The integral of a function of two variables, well, that was the volume under the graph. Okay, so here it's a little a little bit more complicated. It's still the sort of the n-dimensional volume. If you think about the units here, I'm basically summing up a bunch of things. That's what an integral is. Maybe if we're just looking, let's suppose that the units of f were units of length, right? So then you have units of length times the units of volume, well, which is the units of length cubed, right? So this is really what it's giving you is units of length to the fourth power. So it's basically four-dimensional volume, whatever that means, right? And well, it means what it's sort of the same thing that we would think of three-dimensional volume. It's just that we cannot picture it easily. Well, that's just what it is. So if you sort of want to think about it as volume under the graph, well, it is volume under the graph, but it's now four-dimensional volume under the graph, right? Because the graph, think about it, the graph is, I have, the function is defined in some region, maybe on this box over here, and then at each point it has a value. If I want to draw the graph, I need four dimensions, right? Because I need the, this is going to be sort of my base, right? Those are the independent variables, and then I need, one more dimension for the dependent variables. So, well, so the graph is in four dimensions. So the volume under the graph should be four-dimensional. All right. So maybe that's harder to picture. Well, but it's or it's seen as it's not possible to draw graphs of three-dimensional or functions of three variables. Oh well, that's just we live in a three-dimensional world. We're stuck with it. We can't change that. All right. So let's look at how. Well, maybe actually before we get to actually computing things, there's just like before. You can use this to compute volumes, right? So for the box, well, I mean it's maybe kind of trivial. We'll see later on that when we try to integrate in just a moment over some more complicated domains. We'll see something more useful at this. But there's still a way that you can get volumes out of this, and that's if I integrate the function 1, right? So this is the volume of B. Well, volume of B. If B is a box, it's kind of trivial, but later on this B might be more general region, right? And so so you can still use it to compute volumes, right? In some sense, you're putting this one maybe as a unitless quantity, so that you get units of volume. All right, let's try to see how we integrate. Well, if B is a box which is given, where I have maybe X is between some A and B, and Y is between some C and D, and Z is between some. I don't want to use E, since that's sort of the exponential. So I'll use maybe P and Q, right? So if I have this, then the triple integral over the box of some function x, y, z dv. This is really a theorem. The Fubini theorem. That this is the way that you compute. It's going to be a triple iterated integral. A to B, C to D, and P to Q, X, Y, Z. Now this was DZ is the innermost one, DY is the middle one, and dx is the outer one. Now I can do this in any order that I want. Maybe I could do dx, dy, dz, right? But x as the innermost one. Well, that's just over here. Just doing this, right? And same thing for all the other orders. Now again, we can do this, we can change the order here because A, B, C, D, P, and Q are all constants, right? So last time that if we had this iterated integral and one of these if B was not a box, or before a rectangle, it was a more complicated region, and the limits in the iterated integral happen to depend on one of the other variables, right? Our variables that's sort of further out in the integral. Well, then you couldn't just sort of flip the limits, because it would make no sense. And couldn't do anything, with that expression. So it's there. You have to be a little bit more careful. Well, for a box, it's easy. It's just like for a rectangle. We just switch the integrals, right? Just for a box. Let's do an example. Suppose that the box is maybe x is between 0 and 1, y is between 0 and 2, and z is between 0 and 3. A simple box. And let's do the integral over b of xy plus z squared dv, right? Well, let's write it down in some order. Let's maybe put the x in the middle, as the innermost one, y as the middle one, and z as the outer one, right? So we have still xy plus z squared dx dy dz. And so now we have let's solve the innermost integral, right? So x squared y over 2 plus z squared x going from 0 to 1, right? dy dz. Could have done that in an easier way, but let's just do this in the most maybe straightforward way. So I plug in 1, plug in 0. Well, that's easy. 0, 3, 2, and then so it's just basically plugging 1. So I have y over 2 plus z squared dy dz. All right, and we do it again. So antiderivative with respect to y, right? So it's squared over 4 plus z squared y, and y plug in 0 and 2 dz, right? So that's equal to 3. So now I'm plugging in 2 over here. So 2 2 squared is 4, right? So I get 1 out here, and out here I just get z squared, right? And all right, z plus z cubed over 3, square brackets over here, z don't want to put this this in there anymore, right? I'm just solving this. I mean, I'm already one dimension, right? You guys are experts at this. So this is 3 plus 3 cubed over 3, so it's 3 squared. So 3 plus 9. So what's 12? Yay! All right. So it's it's nothing more difficult except just keeping track of things. Now, maybe something, I don't know if I've mentioned this before, but these iterated integrals, this is where you really have to make sure that you figure out what variable you're integrating with, what you're evaluating, and so on. You really want to label everything correctly, because if you don't, you will make mistakes. I've graded enough exams and quizzes and all that to see that if you leave out the dx's and the dy's and the dz's and leave out these guys, you will make mistakes. Maybe not all of you, but everybody will make that mistake at some point, right? So do make sure to write down all the dx's, all the dy's, all the dz's, all that. When you're evaluating, it's a good idea to put not just put 0, 1 over here, because which one am I plugging into? Maybe you have it in your head when you're computing, but it's best to not depend on just what's in your head in any particular time, because then it's impossible to double check your work, right? And it's impossible for me to grade it well, because I don't see in your head, right? So make sure to write down all the detail when you're working this out in an exam, and even if you just need to work this out, maybe in some other class or or in your job or whatever, you want to work out in as much detail as possible so that you can double check your work, right? All right. So how do we? So that's integration over a box. It's basically the same as in two variables. How do we integrate over something more complicated? So it's really the same idea, and we really reduce it to a two-dimensional interval. Let's suppose that we have, let's suppose D is a region in XY plane, some sort of region somehow described in the XY plane. And let's suppose W is a region in 3 space given by, so this is in the XYZ space, right? It's given by, X and Y are in D, and Z is between, maybe let's say alpha XY and beta XY, right? Basically what you have, let me try to draw a picture here. So it's in the XY plane, you have some sort of a region here. Maybe let me draw a simpler region, just so that let me draw a box, right, a rectangle, or kind of rectangle-ish region, so that I can easily draw something above it. So now in the Z direction, we have graphs of two functions. We have Z is alpha x y, and maybe here is Z is beta x y, right? And now the region is all the points in between, right? All these guys between these two graphs, that's W, right? So if I have a region given like this, then the way that we integrate, it's very similar like before. The way that we'll do it is we'll split it up. We'll integrate over the domain, but what do we integrate? We integrate from alpha to beta, right? For any particular point in D, you sort of think about going upwards, and we start integrating at some point. That's basically given by alpha, and we end at beta, right? So we're integrating in the z direction, right? And then we just integrate over all points in D. So z starts at alpha xy and ends at beta xy f x y z. Now the inner integral is the dz integral, and the outer integral, well, that's just however you integrate over this two-dimensional thing, right? Because this thing is that's going to be a function of x and y. Once all the dust settles and you compute what this integral is, for each x and y you get a number, right? Because the z, that will be integrated away. All right. So let's look at an example, and let me start a new page for this example, so that we can we have more space. All right. So let's suppose that I have, what I want to do is, let's suppose that W is given by I wanted to say let D be the triangle bounded by the x-axis, y-axis, and x plus y equals 1 by these three lines, and W is the region I didn't put it above D, between the planes. So now between two planes, and I'll write them as graphs. Z is x plus y, and z is 2x plus 2y. Now, how does this look? Well, in the xy plane, I have the x-axis, the y-axis, and then this line x plus y equals 1 in the xy plane is the line going like this, where this is 1 0 is 0 1, right? So this is my D. Okay, let's look at how this region above looks like. Well, it's really this plane going through the origin, right? Because the origin is definitely in this plane, and then it's hitting the xz plane sort of in a line like this. It's hitting the yz plane in a line like this, and then once it gets out here, this is the bit of the plane above D, right? And it goes out to, you can sort of check what these coordinates are, right? I mean, this point is when y is 0, x is 1, right? That's where I'm here. Then z is 1, right? So this is the point 1 0 1, right? And similarly, this is the point 0 1 1, right? And so I have It really looks sort of like this triangle, right? And then this thing, well, that just makes all the z's bigger, but it's sort of similar idea. And then I go all the way up to 1, 0, 2 and 0, 1, 2, right? That's what I get out of this this formula. So that's the vision. It's the inside. This is sort of I don't know how you would sort of not quite a pyramid, but kind of skew pyramid that's sort of standing on its tip, right? Okay, so let's integrate. How would one integrate the following? I think it's over w. Let's do x, y squared. Let's do something more complicated, maybe less complicated in some way. Let's just some random function, dv. How would we integrate this? So, all right. Well, let's integrate. It's the integral over d, which is going to be the triangle, right? The integral from, well, I know what, so this is my alpha, this is my beta, so x plus y to 2x plus 2y of xy squared plus z dz, the area, right? Let's even maybe, before computing this, let's expand what this d integral is, right? It's let me draw just in the xy plane this triangle d, right? And so you can see, so this was the x plus y equals 1. So maybe if I do let's let x go from 0 to 1. That's this point, right? That is 1, 0. So I'm going to have x going from 0 to 1. That's going to be my dx bit, right? Then y is going to go from 0 to, well, I have to solve for y on this line, right? So y is 1 minus x. Okay, 1 minus x. So that's gonna give me the integral over d, and then I just put in what this integral over z is, right? Is a dz. I have x y squared plus z. All right, and now we integrate. So let's do this. So we have the antiderivative over here, x y squared z plus z squared over 2, and now we're plugging in z as x plus y, and z, so here I don't have to mark it, 2x plus 2y dy dx. Alright, so 0, 1, 0, 1 minus x, and we plug all that in, so we have we're gonna have x y squared 2x plus 2y plus 2x plus 2y squared divided by 2 minus, right, we're subtracting the same thing, just with plugging in x plus y. And let me put in this parentheses because it's very easy to get these things screwed up. So right, that's at x plus y, so let's have x y squared x plus y, and I have x plus y squared over 2. So that's this parenthesis, and then this parenthesis is just this, right? dy dx. That can be simplified quite a bit, because if you think about it, what is 2x plus 2y? It is just 2x plus y, right? And 2x plus 2y squared, well, using this formula again, is 4x plus y squared, right? Well, then that means I have, over here I really have xy squared, twice this guy, right? So I subtract one of them, so I get xy squared times x plus y. Over here I have 4 of these, right? And I have 4 of these, right? This is really 4 times this, right? So I'm left with 3 of those. So plus 3 halves x plus y squared. Okay, that's much easier, right? You put in the parentheses, dy dx. What can we? Well, let's maybe expand the sucker and 1, 0, 1 minus x, and I'm going to have x squared y squared plus xy cubed, right, plus 3 halves, and then I'm going to get x squared plus, then I'm going to have 2 of the cross term, x times y plus y times x, so I'll have 3xy, and then I have 3 halves y squared, dy dx. Whew. All right, let's do this, right? Since we're already at it, why not finish it? 1 minus x. So I have sorry, I wanted to already anti-differentiate. So I have I'm doing with respect to y, right? So if I anti-differentiate over here, I have x squared y cubed over 3 plus x y to the 4th over 4 plus 3 halves x squared y plus 3 halves x y squared plus well, 3 cancels, that's nice, y cubed, and now y is going from 0 to 1 minus x dx. Alright, and I plug in, and we get well, basically we're just plugging in this thing, so we have x squared 1 minus x cubed divided by 3 plus x 1 minus x to the 4th divided by 4 plus 3 halves x squared 1 minus x plus 3 halves x this parentheses 1 minus x squared plus 1 half 1 minus x cubed dx. Alright, now maybe it's now this is just calculus 1, so I'll say left to student. Now you can see maybe partly the point I'm making is that I mean, it can look very simple, but as even for a fairly simple integral, this can get rather tedious quickly. Even though I mean we're just dealing with polynomials in x, y, and z, and so there's no problem. They're very easy to anti-differentiate, but yeah, things things can get out of hand fairly quickly. But all it is just a little bit of calculus, right? There's no it's just turning a crank, right? So that's basically this works. The way that this works. So it's the same as for two variables. If you have three variables, it's gonna actually be the same if you have 5 variables or 20 variables. It's just maybe the physical interpretation of what the integral is gets maybe harder, but integrals over more dimensions do happen. It's not that you only integrate over 2 or 3 variables. But you can already see that here one of the physical interpretation, the 4-dimensional volume, is already a little bit of a stretch of the imagination, right? But there are other interpretations of the integral. For example, one thing that just to end on what sort of application you could do that's not really 4-dimensional volume under the graph is, for example, the average value. So you could think of maybe I have a 3-dimensional space, maybe some sort of material, charged material, and I have charge, and maybe I'd want to figure out the average charge or the average average density, or maybe the average temperature of something, right? I have some value, let's call it f, defined on a 3-dimensional object, and I want to figure out what is its average value, right? And it's very similar to the way that this is defined in 2 variables, or in 1 variable as well. So average of f over w is, well, it's supposed to be 1 over the volume of w, that's the way I'll write volume, times the integral of w, right? Now, this could be, maybe I can write this in a more complicated way. Same thing, this is just the volume, right? So that's one interpretation of the integral, right? That you can compute. It's really averages, right? If I divide by the volume, I get the average value of f, right? And so that's something that I don't have to stretch my imagination to think of 4-dimensional volume, right? Okay, so good enough for today.